The tools that we need for our lesson today, looking at other stoichiometric calculations. Please make sure that you have not only your note pack open to page 5, but you'll need your periodic table, polyatomic chart. We will be writing formulas, of course. I have my stoichiometry roadmap as a great visual of trying to figure out how many steps, where am I starting, where am I going, so please make sure that's out as well. And of course, my calculator. So as we begin today, looking at what we call other stoichiometric calculations, it really is nothing more than conversion factors using our problem-solving diagram. We can solve any category of stoichiometric problems using our stoichiometry roadmap. Remember, in chemistry, when we measure matter, we can count, we can weigh, or we can take a volume. If we're given the number of particles, we see Avogadro's number as the unit of exchange into the mole. Of course, given a gram, it's formula weight. The word is molar mass that leads us into the mole. If it's a volume of a gas, and it must be a gas to do volumes, we use the molar volume value of 22.4. Counting, weighing, or taking a volume, all roads lead into the mole, knowing that any good stoichiometry problem has the heart of want over given and heading back out to the desired unit. The 3 steps of stoichiometry: divide, ratio, multiply. When we look at our notepack examples that read other, what we're saying is that it doesn't matter if I give you particles, mass, or volume. Whatever the unit is, we'll find that correct exchange and head into the mole. Let's take a look at our first example. Reading it with me, it says, how many molecules of oxygen are produced when a sample of 29.2 grams of water is decomposed by electrolysis? Remember, our stoichiometry is only as good as our equation writing skills. I'm noticing the pattern of chemical change is given to me by the word decomposed. The pattern of decomposition suggests one reactant breaking down into simpler products. When I first read my example problem, I tend to just ignore all the numbers and try to pull out reactants and products. Oxygen is being produced. If I think about what that means, on the right side of my arrow, I know oxygen molecules are being produced. They're being produced from the decomposition of water. Water is our reactant. The term electrolysis just simply means to zap it with electricity. Often you'll see that written out as a little lightning bolt. That's the best I could do for that. If this binary compound is decomposing, our helpful hint suggests binary compounds simply break down into their elements when heated or treated with electricity. Water is a binary compound. It's made of 2 elements, H's and O's. And it told us as part of the story problem that oxygen was produced. The other element must be hydrogen. When H's and O's are written, we know that they are diatomic. Remember our sentence, horses need oats for clear brown eyes, and those are the 7 naturally occurring diatomic molecules, of which O's and H's do indeed belong to that club. We have a great skeleton we need to balance. When water decomposes into its elements, the H's come out fine, but the O's aren't balanced. So I back up and correct that by doubling the water and come back to repair the H's. A 2:1:2 stoichiometric ratio balances my equation. Once I get my equation written, I consider that a recipe. Then I go back and I reread the problem for the numbers. It's asking me how many molecules, maybe I'll just bookkeep that and put that right under my target. How many molecules of oxygen are being produced when 29.2 grams of water, and I'll just tuck that under there so I can keep track. I'm given the mass of water in a gram, asked for the number of molecules of oxygen. Given a mass, calculate a molecule. Take a peek at your stoichiometry roadmap. The given is the mass of water. This is our starting point. We want to know all the way over here the number of molecules. That's what representative particles mean, molecules, atoms, or formula units. To move all the way from the left to the right, I can count 3 conversion factors. Step 1, go into the mole. Step 2, mole-mole ratio. Step 3, we're going to use Avogadro to head out to the world of particles. Let's begin by writing what we know. 29.2 grams of water is our given. I like to set all 3 parentheses down so I can see my target. We have to get all the way to the molecules of O2, and I use MLC to represent molecules. Knowing that the heart of our problem is the stoichiometric ratio of want over given. In our first step, to move from mass of given, which is mass of water, into moles of water, we've got to use the molar mass as our conversion. That molar mass of that given compound water. So that first conversion will look like 1 mole of water set over the molar mass of 18. Notice how grams are canceling and we're at the mole unit. This first conversion has moved me from mass to mole, and here I'm standing on the roadmap. To set up our ratio, the heart of our problem, we think want over given. We want to know the oxygen, that's our target. Its coefficient is a 1. On the top, we'll place 1 mole, that's what we want. And on the bottom, we started with water. Its coefficient is a 2. Want over given, our stoichiometric ratio of 1/2. The last thing we need to do is head north in our stoichiometry roadmap. We want to count. We want to count the individual particles. When we go from mole to particles, we trip over Avogadro's number. We see that there is 6.02 times 10 to the 23rd molecules of oxygen in every 1 mole of oxygen. Every number has a label and a unit every step, every time to ensure full credit. Please grab your calculator and follow the key sequence with me. Hit 29.2, our given mass. In the first conversion parenthesis, it's showing us divide by 18. 18 is on the bottom, so we divide. The ratio is 1/2. I hit times 1 divided by 2. The ratio of 1/2. In the last conversion, we hit 6.02. Remember the times 10 to the is second function e, 23rd power. Hit equal and see if we match with 4.88 times 10 to the 23rd power molecules of oxygen. We started with a mass. We went to the number of molecules. The 3 steps to divide, we ratio, we multiply, following the pathway on the stoichiometry roadmap. Let's try another. Read it with me. Example problem. How many liters of oxygen are produced by the decomposition, pattern of change there, decomposition, of 6.54 grams of potassium chlorate? Again, reading it through for the first time, I tend to just ignore the numbers, and I'm trying to pull out the recipe. I don't stand a chance of getting the stoichiometry problem right if I have an incorrect equation. I've got a decomposition pattern of potassium chlorate. I wouldn't think of predicting without pulling out our decomposition helpful hint page. There is a pattern of decomposition for chlorates. Take a look and see if you can find it. When metallic chlorates decompose, metallic chlorides and oxygen gas are released. Everywhere we said metal, you place the word potassium and you'll literally hear the recipe for our equation. Potassium chlorate, when decomposed, gives potassium chloride and oxygen gas. There's the pattern of change from the decomposition. Potassium chlorate, when heated, decomposes to form potassium chloride and oxygen gas. Our skeleton is in place. Now let's balance. K's and Cl's are looking good. It's the O's that are off. If I have 2 on the right and 3 on the left, we'll turn them both into 6's and then go back to repair the KCLs. This stoichiometric ratio is a 2 to 2 to 3. Now let's go back and figure out what we're given and what we want to know. How many liters of oxygen? There's my target, a volume of oxygen. From the decomposition of 6.54 grams of that reactant potassium chlorate. Given a mass, calculate a volume. Chart your course on the stoichiometry roadmap. The unit given is the mass of potassium chlorate. The unit we want is volume of oxygen. To move from the left all the way to the right are 3 steps. Step 1, we'll divide by molar mass. Step 2, we ratio want over given. Step 3, we come down to the world of volume, where 22.4 liters, our molar volume, exchanges moles into liters. Step 1, Step 2, Step 3, let's set up our parentheses. Our given mass, 6.54 grams of KClO3. I like to get my parentheses ready so I can see my target. We want to land at liters of O2, the heart of our problem, the want over given ratio. In our first step following the roadmap, notice we need a molar mass. Turning grams into moles requires a formula weight for our reactant potassium chlorate. 1 mole of potassium chlorate set over potassium weighs 39, 35.5 for the mass of a chlorine, and 16 times 3 for the 3 oxygens. That looks like 122.5 for the formula weight. A want over given ratio, we want to know the moles of oxygen. 3 is its coefficient. Remember, our target is the oxygen. 3 moles of oxygen are produced for every 2 moles of potassium chlorate. We want over given ratio. Step 1, we divided by molar mass to go to the mole. We set up a mole-mole dance, a want over given ratio, and now I'm standing here. Remember the desired unit? We want to know liters. Head down to find the volume of what we want. When we go down to find volume, we see that molar volume is our exchange. We know that 22.4 liters of oxygen is equivalent to 1 mole of oxygen. We divide, ratio, multiply, the 3 steps to stoichiometry. Hit it with me. Very important you become confident with your calculator skills. Start with the 6.54, the grams of given. Step 1 in the conversion says divide by that molar mass of 122.5. We'll multiply that by that ratio of 3/2. That's typed in by saying times 3/2 times 22.4, the molar volume, and we find 1.79 liters of oxygen. Let's keep going. A next example. Assuming STP, how many liters of oxygen? And notice here, this is nice. They've given us the equation, so I don't have to work that part out. So I'll just tally what we're being asked to solve for. How many liters of oxygen gas are needed to produce 19.8 liters of sulfur trioxide in this balanced equation? Given a volume, calculate a volume. A volume-volume problem. Our journey would start at volume and have us go to volume. 3 steps to move all the way from the left to the right. A volume-volume problem. Let's get our parentheses ready. The given quantity of 19.8 liters of sulfur trioxide. There's our given. A step 1, step 2, step 3, where the heart of our problem is the mole-to-mole ratio. And we can see our target as liters of oxygen. A volume-volume problem has me begin with volume of given, and we're going to use that molar volume of 22.4 liters to bring it up to the mole. Right here, 1 mole of given set over the molar volume becomes our first parenthesis. We know that 1 mole of sulfur trioxide would be 22.4 liters big. We want to know oxygen. Its coefficient is a 1. A want over given mole ratio, where those moles are being pulled from the balanced equation. If we want oxygen, it goes on the top. We started from sulfur trioxide, it goes on the bottom. We have a 1/2 ratio. To head back out to the world of volume, notice we're right here. We come down and head back out to the liters of want. 22.4 liters of oxygen for every 1 mole of oxygen. Now notice something very unique to a volume-volume. In step 1, I'm dividing by 22.4. In step 3, I'm multiplying by 22.4. Since our conversions are the same, they are going to simply simplify. With a volume-volume, if you look at your pathway, volume-volume is going to have us divide by 22.4 and multiply by 22.4. That's a unique scenario. Let's hit that out. We have 19.8 times, canceled. We're into the step 2. We need times 1/2. That's 9.9 liters. Now again, this is unique to a volume-volume. I'm dividing by a conversion factor that I'm later multiplying by 22.4. Those will simplify. We have one more on our page. Let's take a read together, please. Read it with me. Nitrogen monoxide and oxygen gas combine to form the brown gas nitrogen dioxide. Let's pause there and get those words into a recipe. Nitrogen monoxide, NO, and oxygen gas combine to form nitrogen dioxide, NO2. Here are those prefixes for these molecular compounds. Let's get it to balance. I have 3 O's here, but only 2 on this side. Let's start by doubling. 2 N's, 2 N's, 4 O's, 4 O's. A 2 to 1 to 2 stoichiometric ratio. Now let's continue reading. We have our recipe set. How many molecules of nitrogen dioxide are produced when 3.4 liters of oxygen react with excess amounts of nitrogen monoxide. Given a volume, calculate the number of molecules. Chart your course. Given a volume, we've got to get up to molecules. A volume molecule problem. Step 1, Step 2, Step 3. The 3 steps to stoichiometry. Let's begin by writing what's given. The 3.4 liters of oxygen gas. Get our 3-step conversions all set. And now we can see the target is molecules of O2. No, it's not, it's NO2. Glad I caught that. Given the oxygen, we want the nitrogen dioxide, the molecules of NO2. I'm going to rewrite that so it's neater. Molecules of NO2. That's our target. Step 1, we're at the volume. Given a volume, I need to bring it to the mole. I'm tripping over the molar volume conversion. Given a liter, use the molar volume of 22.4. We know that 1 mole of oxygen would be 22.4 liters big. We want over given, the heart of our problem. We want to know nitrogen dioxide. Its coefficient is a 2. Starting with moles of oxygen, its coefficient is a 1. The stoichiometric ratio of 2/1. Here we are on our roadmap at moles of what we want. We want to count the number of particles. To go up to the world of molecules, we use Avogadro on our conversion. 6.02 times 10 to the 23rd molecules of NO2 is equivalent to 1 mole of NO2. Let me get that on the screen a little better. Starting with the volume, we divide, ratio, multiply. Please hit it with me to become confident with your calculator. Start with the given amount of 3.4 liters. Divide by the molar volume, 22.4. For the ratio, we have 2/1 times Avogadro's number, 6.02, second function e, to get that times 10 to the button, 23rd power. And I'm finding 1.8, I'll say 1.83 times 10 to the 23rd power. Before you flip your page, I want to see you give yourself an A+ so that I know you listened to the entire page. When I see this A+ on your paper, I know you've gone through the videos. When that's completed, pause here and we'll be turning the page.